Hi guys, so today you will learn chapter 10. This is the final chapter for analytical chemistry and with title Redox titration. Okay, now let's look for the expected outcome for this chapter. Students should be able to understand the redox reaction concept uh, and also apply the redox reaction concept in problem-based questions. Uh, Besides, the student also will need to calculate the potential or as a signal in any kinds of reaction by using Nernst equation. So this is the outline for this chapter. So we will go through the oxidation reduction reaction. So basically, redox reaction consists of two main reaction, which are oxidation and also reduction reaction. And the second one is redox titration curve. So basically, you will learn about the um, uh, how you should calculate uh, the endpoint and also the equivalent points. Okay. Next, what types of indicator that basically use for the redox reaction, and the last one is the application of redox titration. Okay, so before we start, let me remind you that redox reaction consists of two types of reaction. The first one is oxidation, and the second one is reduction. So let's look for this example: the cesium ion and the iron ion in this example. So basically, when we talk about oxidation reaction, the half a cell will be contained with the reducing agent. Okay, whereas for the reduction reaction, in the half reaction, it must consist of oxidizing agent. Okay, so basically what you need to know that for the oxidation reaction also, you will lose an electron, whereas for the reduction process, you will gain a certain amount of electron. So for this example, when you try to see the overall reaction, this is what we call as the overall reaction. What you can see is the cesium ion is accepting one electron. So it changed to cesium 3 plus. So here you can see that there is a one electron was added. Okay, so in this case, this cesium is actually the oxidizing agent. Okay, whereas for the ion, so you can see from the 2 plus charge, it become 3 plus charge. So basically, you will see that this half cell is lost about one electron. Okay. So when it lost one electron, so we can estimate that it is an oxidation process, and iron is actually the reducing agent. So now you have the overall reaction, and from the overall reaction you have also the half reaction. So basically when we focus on the half reaction, we need and we require to balance the oxidation reduction equations. So first of all, when we want to balance the equation, we call it as a half reaction method. Okay, so basically the first step is to assign oxidation numbers so that if you can see the oxidation number change from reactant to product, so you need to estimate that value. Either it lost 1 electron or gain 1 electron. Okay, so when you have this kind of concept, you can estimate that it is oxidized or reduced. Okay, now we go for the second step. Write the oxidation and reduction half reactions. So basically, when you write the half reaction, uh, there's always electron involved in each of half reactions, so you need to be careful. So here you need to balance each half reactions. For instance, if the reaction is for the oxidation is 2 electron, and the reduction process is 1 electron, so the half cell for reduction needs to times 2, so that 2 electron will be transferred through the oxidation and reduction process. Okay, so you need to balance the number of electron that transferred. Okay, next you need to balance the elements other than hydrogen and oxygen. Okay, so you need to see very careful if there is other than hydrogen and oxygen atoms. So you need to balance first that elements. Okay, now when we go for the oxidation, you need to balance the oxidation by adding water molecules, H2O, and whereas for the hydrogen, you need to add H plus, or we call as proton. And the next step is you just need to balance the charge by adding the electrons, and then you can get the overall reactions. Okay, so now next is multiply the half reactions by integer so that the electron gain and loss are at the same. So this part is what you need to see very careful, so that you will not lose any electron in the overall reaction. Okay. Next is add the half reactions, subtracting things that appear on both sides. Okay, if you see on the reactants part, there is H2O, and also in the product part, also H2O exists. So what you can do is that you just need to subtract these two molecule from the overall reactions. Okay, because they are the same. Next is make sure the equation is balanced according to mass. Okay, so just you need to see carefully the number of atoms, the number of um, hydrogen, oxygen, and also your elements are in the same number in the reactants part and also in the products part. Okay, so the next one is make sure the equation is balanced according to charge. So you can check, okay, you can recheck either the total charge of reactants is similar to the total charge of the products. Okay, so this is the standard potential that basically we will use when we want to answer any questions like in test or in final examination. So this equation will be given to you if it's necessary, and you don't have to worry. Okay, so you can see uh, the hydrogen 2H plus 2 electron produce H2 gas is actually the potential is a 0. Okay, and when you go up, the value become more positive, and when you go down, the value become more negative. So what we can estimate from this is actually the more positive the potential, the better oxidizing agent is the oxidized form. Okay, so you need to know when you have uh, more positive value of potential. So it is a better oxidizing agent. Okay, so when it is a better oxidizing agent, it means that that elements will undergo a reduction process. Okay, okay, so that is the concept that you need to know, okay, before you can answer any question that relates to the redox reaction. So I hope that you can take note, and the same things, the same concept for the more negative of potential. So I hope that you can please understand this very well, and don't worry about the table. You don't have to memorize all the value, all the configuration. You just need to know how to balance it and how to calculate the potential, okay, at endpoint or at equivalent point. Okay, now let's look for the standard cell potential terms, okay, or the symbol with E not cell, okay. So basically, I just call it E not cell. So I hope that you can understand that I refer to the standard cell potential. Okay, what is E not cell is the difference between the standard half cell potentials of the cathode and the anode. So basically, when we do a redox reaction, we are focusing on these two different uh, um, electrode. Okay, we have a cathode and also we have anode. So basically, when we do calculation at standard state, okay, so we can simply use these two formula that you can see, okay, that you can see from here, okay, is the same, okay, is the same. So the first one, if you if you can understand very well when you use the first equation, so you don't have to worry to understand the second formula, because it's totally the same. Because you need to know that at the cathode there are always a reduction occur, okay, whereas for the anode there is always oxidation process occur. So this is just the difference between when you want to use in calculation, when you want to refer cathode, the electrodes, or the process. It depends on you, okay. Okay, now consider this example. Calculate the cell potential for the oxidation of zinc solid by a silver plus ion in aqueous solution. So basically you have this is what we call as a overall reaction. This is overall reaction. So from this overall reaction, you can simply determine the process. And when you can identify the process, okay, you can exactly know uh, where does the process occur. Okay, so let's say for the reduction process, uh, it will undergo at the cathode electrode. So this is what the concept that you need to understand very well. Okay, so at the reduction at the cathode, okay, the reduction occurred. So when we talk about reduction process, you need to refer back to the table that I mentioned just now. This table gives you the value of a silver ion plus electron produce the silver solid. So here the E naught value will be given to you, and uh, you need to do the same thing for the oxidation process. Okay, so this is exactly the same process that you need to know. So basically at the oxidation process, you can see the value change. Why does this value change? Because the table value is a potential for reduction process only. Okay, so when it comes for the oxidation process, you need to change the sign. Let's say if the in the table the value is negative, so you need to change from negative become positive. Okay, so this is the answer for the oxidation process. So the E naught is actually positive 0.76 volt. Okay, so uh, by the time you want to calculate the inner cell, so you just simply add and 0.8 volt plus 0.76 volt, you get 1.56 volt. Okay, now let's look for the cell potential and free energy. So basically the concept of cell potential, when it comes to the explanation on the molecular level, so you need to understand that we need to relate it with the free energy. Okay, the free energy change in the solution. So basically from the equation of free energy change, so we can see delta G is the free energy change. So it equals to negative the multiplication of the number of moles of electron transferred uh, and the Faraday charge on 1 mole of electrons. Okay. However, this equation is very general and commonly we not use it in analytical chemistry a lot. Okay, so this is just for your information. Okay, now let's look for the Nernst equation. Nernst equation is actually the derivatives from the free Gibbs energy formula, and the general equation is this one. Okay, so in this formula, you can see the E cell equals to E naught cell. Okay, minus R. R is the ideal gas constant, 8.314 joule per Kelvin per mole. T is actually referred to the temperature in unit in a Kelvin unit. N is the number of electrons that transferred in the process. F is the Faraday value, 96485 coulomb per mole of electron. And ln Q. Q is the product divide reactant. Okay, so basically the formula after we include the value at 25 degrees Celsius, so you will get this formula. Okay, okay, now let's look for this example. The solution is 10 to the power of minus 3 molar in chromium ion and 10 to the power of minus 2 molar in chromium ion. If the pH is 2, what is the potential of the half reaction? So when you have this full of reaction, so you need to identify either it is a reduction or oxidation. So basically it is a reduction because this uh, process you can see that the number of electron like 6 on the reactant, so this is the reduction process. So now let's look for the how for the solution on how to calculate the potential of half reaction. So you need to write your answer uh, in an organized way, and you can see for this example in the slide. And the first step is you have the pH value, so you can identify easily the concentration of proton. So after you use it, use the formula negative log H plus. So the concentration of proton is 0.01 molar. And now you need to calculate the E cell. So based on the nurse equation, you can easily use the formula that we already looked in the previous slide. And you need to know that N is the number of electron transferred and Q is the ratio of product towards a reactant. So in order for you to understand what is E naught, so you need to know and you need to refer to the table of the half cell reaction. And you can see that in the overall reaction, the E naught is 1.33 volt, okay, from the table. And now how to calculate the E value, the potential value of the half cell reaction is equals to 1.33 minus with 0.0592 divide 6, because you can see the number of electron transferred is 6 log and then you times with log product, the concentration of product, okay, the concentration of product, the concentration of chromium 3 plus divide to the concentration of proton to the power of 14, and then times with 1 times 10 to the power of minus 3. This is the concentration from the chromate ion. So at the end, you will get 1.06 volt. That is your answer. Okay, so now let's look for the titration curve that involve in the redox titration process. So basically, when we have the two elements in the mixture, so you can easily identify the equivalent point. So this is the titration curve. I mean the common titration curve, and the signal. The difference is the y-axis is the volt. I mean the potential. Okay, in units volt. That's why you need to use the Nernst equation in order to calculate the potential, because on the y-axis is the potential value. Okay. So on the x-axis is the volume of your titrant. Okay, now we consider this example of process, and we have the standard electropotential that we can get from the table. Okay, so this is all the both are in a reduction process in this half cell equation. So you need to be careful in any kinds of redox reaction. It does involve reduction and also oxidation. So you need to be careful. Okay, next, the point in the redox titration is you need to identify before titration, prior to the equivalence point, at the equivalence point, and after the equivalence point. Okay, now let's look for the redox indicator. Okay, so basically any indicator that can be used in a redox reaction also can be used like the one that you use in the acid-base titration, complexometry titration. It can be any. Okay, so you don't have to worry what types of what is the indicator that you will use in the redox reaction, because you must know in the acid-base titration, also in the complexometry titration, electron will be transferred. In any process, there must be electron transfer. Okay, so you can use any kinds of indicator for the redox reaction. Okay, so basically this is just the explanation for the indicator, and the same concept that you need to implement in this redox reaction is that uh, you will observe the color changes, okay, um, in the oxidation solution and also in the reduction solution. It will give you a different color. So this is what you need to take note. Okay. Okay, now we go for the last part of this chapter, the application of redox titration. So in this application, we have two types of analysis, the inorganic analysis and also organic analysis. Okay, for inorganic analysis, for instance, the determining of the total chlorine residue by using oxidizing power of chlorine to oxidize iodide ion to triiodide ion. The amount of triiodide ion is determined by back titrating with um, S2O3 2 minus ion. Okay, so in the organic analysis, for instance, the analysis of ascorbic acid, okay, which is the active functional group in the vitamin C, by oxidizing the anidyl functional group to an alpha diketon. Okay, and the other example of application is determination of the chemical oxidation demand, uh, we call as a COD, of natural waters and wastewaters by a refluxing sample in the presence of excess potassium chromate. The excess of potassium chromate is determined by back titrating using ferrous ammonium sulfate. Okay, so uh, the COD provides a measure of the quantity of oxygen necessary to completely oxidize all the organic matters in a sample to carbon dioxide and water molecules. Okay, so this is a few example of application for the redox titration. Okay, so uh, that's all for chapter 10, and thanks for watching. Bye.